All right. This is my second attempt at recording an acceptable product. We're going to present, or I'm going to present, introduction and materials for this lab for CH203, molar mass by freezing point depression. So first thing, where to find the information that you need to do this lab. It is in Blackboard, and it will be under lab number 8. And I will share a couple of screens and show you what it will look like so you know that you have the right material. So let's share this one. Okay. There's the lab. Notice we have a pre-lab question. And actually, we're going to go through that one in the presentation. So if you pay attention, you'll be able to answer this one just by watching the video. Notice we have an activity 1, activity 2. And then activity 3 is what do you do with the data you gathered in activities 1 and 2. And we're going to go through those, and I'll show you how. In fact, the pre-lab question shows you how to use the information that you get from activity 1 and 2. Then you have these laboratory questions, and those I'm going to leave up to you. Possibly you might get that information from the discussion that I'm going to give you. So that's the hard copy lab. You need to print that out. And then you're going to need data. All right, so here's your data. Right, this data was gathered by a previous CH203 class. In fact, a little over a year ago by now. It's very reliable data, so you'll notice that this section over here contains the data you need for activity 1, and I'll explain what that means later. This section here contains the data that you collect for activity 2. And this is a partial working out of what you do with the data. And then some hints down here that gives you actual masses that you'll need also. And then down here, the accepted value for benzoic acid, which is the target. We want to determine experimentally the molar mass of benzoic acid, and then you'll compare it to this value down here using your percent error calculation. Okay, so now let's get to the discussion. Freezing point depression. Freezing point depression is a property that may be grouped together with other types of properties that are similar, and they're called colligative properties. Okay? So what do we mean by colligative property? In chemistry, colligative property means any property that is measured with no concern for the material of interest. So that's kind of vague. Let's use an example. In our case, we're going to measure freezing point of a material. In fact, the first material we measure freezing point of lauric acid. And I'll describe that a little later. Lauric acid. Then we're going to add benzoic acid to it and do the experiment all over again and determine the freezing point for the lauric acid, benzoic acid solution. Now, what we mean by colligative property in this case is that it doesn't matter what benzoic acid is. It could be anything as long as it dissolves in the lauric acid and it's non-volatile, because anything that's volatile will evaporate from the surface of the lauric acid, and then you've lost your solution concentration, which is required. It has to be constant through the experiment. So if it's volatile, you're just out of luck. So it needs to be non-volatile, and it has to be soluble in the lauric acid, and benzoic acid is soluble in lauric acid. But we could use, if we wanted to determine the molar mass of something else, we would dissolve it in lauric acid and determine the freezing point before we add it and after we add it, because we're interested in the difference in freezing point. So it's a colligative property because benzoic acid, it works for that, it would work for anything else, and the same property holds. The only thing that changes, the only thing that would change, is if you change the solvent, which is lauric acid. If you change it to some other solvent, then the colligative property still holds, but the quantitative measure is a bit different. Right. So freezing point depression is one colligative property, and I'll just give you the other three common colligative properties so that if you ever run across them, you'll recognize them as such. There's also boiling point elevation. Then there's, let's see, vapor pressure. Depression. That just means the vapor pressure of a liquid has a value if it's pure. Then if you add something to it that is non-volatile, then the vapor pressure will be depressed. It will be lower after you add than before you add. And this is quantified by Rayleigh law. We studied that one in the lecture part of this course. And then the last one is osmotic pressure. Okay, so the one we're interested in is freezing point depression. I could have given you a lab exercise based on any one of these, and it would still teach the same principles of a colligative property and allow us, using any one of these, to determine the molar mass of a compound. Right? It's just that freezing point depression is the simplest version. It's the easiest one to do, so it made sense to pick this one. All right. So we know what colligative properties are, and we know we're going to use the colligative property, freezing point depression, to determine the molar mass of benzoic acid. All right, so what's the quantitation of freezing point depression? Well, we're going to use a formula. And the formula depends upon a change in freezing point temperature. Right? So there's your freezing point temperature. So you have a freezing point temperature initially, that is, without the added solute. And then we determine after we add the solute, and we get a difference. Right? And the difference is expressed as delta. So we get a change in freezing point between activity 1 and activity 2 in our case. Now, the interesting thing about this difference is it doesn't matter what the sign is. We know that it's going to be a freezing point depression. In other words, the freezing point is going to decrease after we add the solute. But we only care about the absolute value. How much did it change, right? So we make that an absolute, right? Just take the sign out. Now that's going to be equal to a product. And the product is one constant, right? That constant is constant for the solvent. So lauric acid will have a value associated with freezing point and a calculation of depression. Right? So this is the constant for freezing point for lauric acid. Right? The other factor that we multiply by that is the concentration of the solute, benzoic acid. Right? And notice I use a small m. Right? Well, why do I use a small m? Well, there's a good reason for that, obviously. Normally, what's most commonly used to express concentration is molarity. You remember molarity? Big M. It's moles per liter, right? So moles per unit volume. Okay. The problem with using molarity in this type of experiment is that the temperature is going to change. That's what we want. We want the temperature to change. But what we don't want is for the concentration to change. The concentration needs to be the same at every temperature within the range of measurement. Right? And if you've got volume as part of your expression and the temperature changes, the volume is going to change. Right? So we can't use molarity. We have to use another expression that is constant over temperature change. So this one is going to be moles. Now this is moles of solute per liter of solution. Okay? This is moles of solute. So that didn't change. But now instead of volume, we're going to use mass. And this is per kilogram of solvent. Right? So this expression not only has volume in its quotient, but it also has the volume of the solution. So that includes the solute and the solvent. Whereas in and this is called molality. Not molarity, molality. Moles of solute per kilogram of solvent. So in the denominator, there's nothing referencing the solute. Now, it's two differences between these measurements. Solution total here and volume. Mass and not total, just the solvent. So this is the one we're focusing on. This is the expression we're going to use in that calculation. So let's be sure our units of measure. You know, I'm a stickler for units of measure, and units of measure and the highbrow way of discussing that topic is a blank mind. Dimensional analysis, which means keep track of your units. So, if the temperature change is going to be what? Degrees centigrade. Right? Units of measure. We already described molality as moles per kilogram. Okay? So, what will the units of the constant have to be in order to give you degree C as your answer? Well, you need to have moles on the bottom here to cancel, right? You need to have kilograms on the top to cancel. And you need to have degree C on the top to be here, right? So the units of our K value are degree C, kilogram per mole. Sometimes, if you look these values up, and they're listed in reference manuals, they may be expressed this way. Degree C, m to the minus 1. This just means the inverse of molality, right? If this is molality, then this is the inverse of molality, right? So there's really no difference. I like expressing it this way because then you can see the cancellation. But reference manuals, trying to save space, you know, because they got lots of information to publish. So our units of measure are going to be that. I'll leave that there for a second in case I need it. We've talked about the difference between molarity and molality. I've used the term solvent and solute. So we know that our solvent is going to be lauric acid. Lauric acid is a fatty acid. Right? There are good fatty acids and bad fatty acids, physiologically speaking. The saturated fatty acids are supposed to be bad for you, but that's a relative term. You need some saturated fatty acid, so don't cut them all out of your diet. It's virtually impossible to do that anyway. Then, of course, there's the unsaturated and polyunsaturated fatty acids that are supposed to be good for you, and they are good. But lauric acid is a saturated fatty acid, and it's really a good one for our purpose because of its freezing point. Right? And of course, what does freezing point mean? The point at which a liquid turns solid. Well, that same temperature is when the solid turns liquid when you heat it up. Right? So it could be melting point as well. So melting point, freezing point are synonymous. They're the same temperature. For lauric acid, that temperature, the accepted value is 48.3 degrees centigrade. Right? So 48 degrees centigrade is well within the range that we can develop easily in the laboratory. All you need is a boiling water bath. Right? And you can put your lauric acid in a tube and stick it in the boiling water and it'll melt. Right? It'll become liquid. Then, I'll go through those details in just a minute. Let's get this out of the way first. Lauric acid, all right, so it's a fatty acid, right? Has 12 carbons, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And this last carbon, so it has a double bonded O and an OH on it. That group right there is a carboxylic acid. Right? It's an organic compound. That's why they call it an acid. Okay? And each one of these represents a carbon. So there are 12 carbons in the acid group. So that's our solvent. Our solute, the compound that we're trying to measure molar mass for, is benzoic acid. So the solute equals benzoic acid. Okay? It's soluble in lauric acid at virtually any temperature. But its melting point is 122 degrees. So we couldn't use easily benzoic acid as our solvent, right? Because it's difficult to develop a temperature higher than 100 degrees in the lab. You can do it. Of course, oil baths would be good, and sand bath would do it, right? But we're interested in safety, and the lower the temperature you can operate at, the better. So this is our solvent. This is our solute. Now, even though this is 122 degrees pure, when you dissolve it in this, its only effect is on the freezing point of the mixture. So while this probably has some influence, it's going to depress the freezing point. Actually, you would expect if you're going to add high temperature to low temperature, you would get some temperature in between, but it's not that way. That's not the way it works. This doesn't matter. When you add that to this and it goes into solution, it depresses the freezing point. So benzoic acid. You've heard of benzene, right? It's on the EPA and OSHA's bad list. But benzene is a cyclical compound, like that. And it's aromatic, so that we represent it with this, right, 6 carbons. And then it has an acid group over here, right? Just like the lauric acid. It's got the carboxylic acid group on it. That's benzoic acid. So knowing that formula, right, you know the structure, you could calculate the accepted value for benzoic acid. Right? It's got 7 carbons. It's got, well, convention. You don't know organic convention. So it's got 6 carbons in that ring. And then it's got a carbon out here. So that's 7 carbons. Then it's got 2 oxygens. And it's got 1 hydrogen out there. But all these other 5 carbons that don't have the subgroup on it also have hydrogens. Right? So you have a hydrogen here and 5 here. So you have 6 hydrogens, 7 carbons, 2 oxygens. And with that, you can calculate the accepted value of benzoic acid. But I've already given it to you anyway. It's in that data picture. Okay. So let's go to the next step. Let me see. I'm going to need some more room, I'm sure. So let me erase this. All right. And let's go to the next item on the agenda. Describe the exercise. All right, so we know the theory behind it. What we need now is how do you do it? So you need certain materials. You need a boiling water bath. Right? And let's put it down here. Right? There's your beaker. There's your water. There's your bubbles. And there's your hot plate. So we got a boiling water bath, which at our altitude will be something less than 100 degrees, but not much. It'll be hot enough. And then you need a ring stand, right? So you need a ring stand, and you need a clamp, adjustable clamp, to hold your test tube. And you're going to have a large test tube. Right? So we have our test tube. Let's see. We're going to grip it toward the top so we can submerge as much as possible in the bath. Right? And I believe the tube we were going to use in class is like 20 by, or 30, probably 30 by 200 millimeters. It's a big tube. Now into this tube, before you actually put it in the water bath, of course, you need to add, through a funnel, a certain amount of your lauric acid. Right? And we use a wide opening funnel. It's called a powder funnel, to add our components to this tube, because we don't want any of them to be up here around the top of the tube, right? Because that part of the tube is not hot. And you need everything that you put in the tube to melt. And when we add our benzoic acid, it's got to go into solution, and the concentration is critical. Okay? So we have our lauric acid in the bottom, and it melts. Right. You take the funnel out, and in its place, instead of the funnel now, we want a thermometer. Right, we got to measure the temperature, otherwise the whole experiment's a waste. So, you can use the thermometer, if you're careful, to stir what's in the tube, because you want it to be well mixed as it dissolves. And then you pull it out, pull the whole thing out. And usually you just loosen the screw here and swing it around out of the heat plume that's coming up from your boiling water bath. And then you measure the temperature. And you watch the temperature. Initially it's going to be pretty high, maybe 80, 75 or 80 degrees. And it's going to, measuring temperature at that point is kind of a waste, because you want the temperature at the point when it changes from liquid to solid. Right? So the method says wait till 60 degrees. Right? So you're going to have temperature column over here, and you're going to have time over here in seconds, and temperature in degrees C. Right? So at time 0, you're going to start your watch. That's one of the lab partners is going to start the clock, and don't stop it. Just let it run. And every 30 seconds, take a measurement. Right? So the initial measurement, let's just say we actually start at 60 degrees centigrade. And then at 30 seconds, you take another measurement. Say it's 58 degrees. And then at 60 seconds, maybe it's down to 55. And you just keep going. And down here somewhere, at this time and this temperature, maybe 48, you find that you start to see the solid appear in the liquid. The melted lauric acid will start to show. Technically, they're not crystals, but see pieces of solid develop. Now, you want the solid to be in the liquid, right? If it starts to occur around the top of the liquid or on the inside of the tube, then it's not at that temperature. That's why we need to keep stirring it too, and only stop periodically to look for those pieces of solid that are starting to develop. It needs to be well mixed. Then you'll notice the freezing point at this time. And we know that the accepted value is 48, so temperature should be somewhere close to 48. And then you keep measuring, and the temperature might decrease. Actually, it shouldn't decrease. Once you reach the freezing point, it ought to stay the same. Right? That's one of the indicators that you're at the freezing point. Right? Remember experiments that we did using an ice bath. Right? If you have solid water, ice, and liquid water together at the same time, then the stable temperature there will be the freezing point. Right? So when you have solid and liquid together, that's the freezing point, and the temperature will not change. Okay? So then you're going to go back, and I think the data says that we put 8 grams, or 8.000 whatever grams of lauric acid in there. Right? Then you go back and you resubmerge your tube in the boiling water, dissolve it again. And while that's happening, one of the lab partners goes over to the balance, probably the same one that weighed out the lauric acid. You get to weigh out the benzoic acid. And the benzoic acid, you don't need as much, right? So maybe 1 gram is enough. Right? The data sheet that I gave you will tell you exactly what mass it is. Mass for both of them. And then you submerge it. You put your powder funnel in there, add the material, and keep it stirred up and submerged in the water bath until it's all melted and mixed together really nice. So you have a solution, a homogeneous mixture. Then once you've melted everything, and the temperature is probably up around 70 or 80 degrees, then you pull it out, do the same thing all over again. Start at 60, keep going. Now when you get to the freezing point of this one, when you start to see solid appear, you would expect the temperature to be something less than 48, maybe 42, something like that. So you're going to get a different freezing point, less than the one you started with. Right? And the data point that you're interested in, once you get those 2 freezing points, is their difference. How much did they change? And we don't care about the sign. Remember, it's an absolute value. All right, so that's the hands-on part. You got your data now. Now what do you do with it? All right. First of all, to show you what you would do with it, I need a different board because you're going to graph the data, right? So you're going to have, let's start about right here. Let's say that's our origin, 0, 0. And then, let me use a ruler because I never can draw a good straight line. All right, so we're going to have there, here, all right. So we're taking measurements at time intervals. So time is going to be on the x-axis. All right. And temperature is going to be on the y-axis, degrees C. Right? And then you need a title for your graph. Right? Say freezing point of lauric acid, and you'll have to write that out, of lauric acid or benzoic acid plus lauric acid. Because we're going to graph both of them on the same. Let me be sure. Hold on a second. Be consistent. Yeah, plot them on the same graph. That's what the method says. So the first one you're going to plot, so as time increases, temperature decreases, right? It's going to be this way. Right, so we'll notice that over time, we'll have maybe 30, let's say 30 there, 60, 90, 120, 150, maybe 180 seconds. Okay? And then temperature, since we're starting at 60, let's subdivide it up so we put 60 way up here. Okay? How would that do? We did 60, 50, 40, maybe 60 here. And let's start up here. 60 degrees here, then 50 here, and 40 here, and then 30 here. So technically, that's not 0, 0. That's 0, 30. But it's okay because we're gonna get what we need from the graph. So what we notice is, over time, 60, we're going to start out at 60 degrees times 0. Right? So it's going to be right there. And then maybe at 30, we're going to get, I don't know, 50, something like this. And then maybe 60, we're going to get something like that. And then what we'll notice is right about here, 90. Like that. So you get roughly a straight line here. And then at this point, we're going to get, 90. We're going to get here, here, no, not there, here, and maybe here. Go out that far. All right, so it's going to be like that. So this is your freezing point. The thing about graphing is it's not perfect. It might be like that as you graph the data. So if you were to have a curve right in this region, how would you determine the actual freezing point? Well, you take this part of the line, okay? Let's just say it's off a little bit. Right? And this part of the line, right? And where they cross is your freezing point. Okay? That's how you overcome that little curve that might develop in your data. Okay? But you also have your observation, right? You were watching, if we were doing this hands-on, of course, and you were watching the tube, then at a certain time, you would notice the appearance of solid suspended in the liquid, very fine particles. And you would call that out, the observer would call that out, whoever's recording the values would make that note. Okay? So when you look at the data sheet, you'll probably see an FP on the data next to that. I still want you to graph the data, but the FP on the actual data numbers confirms that's the point, freezing point. For each one, you have a different freezing point for each activity. Remember that. Okay, so then you graph the other one, and it might come down here, somewhere in here, before it straightens out, right? So there you have a freezing point, and there you have a freezing point. And there's your difference. That difference in temperature is what we want. Okay? So, and we set that aside. So now that we have the initial temperature and the final temperature, gives us that, and we don't care about the sign, so it's like that. Now we have a value for our change in temperature. Right? What do you do with it? Right? So you have this value, right, for the freezing point. Actually, they're two different things. This freezing point. How about that? Is equal to the K value, right? And you need a K value for lauric acid. And that value is 3.90 degrees C kilogram per mole. So that's what would go in your K for this experiment. And the molality is your unknown. You don't know what it is, right? Because you don't know how many moles of benzoic acid you actually put in that tube, right? So you can't calculate the molality. So we're going to solve for this one. So you get a value here, a constant here, solve for the M, right? So the M is this one divided by that one, right? So let's just take an example. Say the difference is 6 degrees, right? So if it's 6 degrees C divided by 3.90 degrees C kilogram per mole, then the degrees cancel, and this expression flips, right? That's in the denominator. This is actually the numerator, right? The denominator of the denominator is the numerator. So that flips. And 6 divided by 3.9, let me just do it. Right? Got nothing but time. So 6 enter and 3.9 divide is 1.538. 1.538 moles per kilogram, which is equal to molality, right? So there's molality. All right, how does that help us? Well, look at it this way. What do we want? Right? What's our guiding principle? Molar mass, right? So molar mass, I often abbreviate it molecular weight. That shows how old I am. Molar mass is equal to mass in grams per unit mole, right? So if we know the mass of our benzoic acid and the moles, we can calculate molar mass, right? Do we know either one of those yet? Well, yes, we do from the data. We know this one, right? Because we had to weigh it out, right? And it was something close to a gram. So let's just say, for argument's sake, that it's that many grams, right? What we don't know is moles. Look at there. We got moles in here. We need to get it out. So we've used that expression to give us molality. How do we get moles out of that expression, right? You need a conversion factor. Or you need a multiplier of some kind. So if we got 1.538 moles per kilogram, this is moles of solute per kilogram of solvent. What would give us moles of solute if we know how many kilograms of solvent are in that tube? And we do know that, don't we? Of course we do. We weighed it out. Lauric acid, we weighed out about 8 grams. So let's just, for argument's sake, it's exactly 8 grams. But that's grams, and this is kilograms, right? So we better change that to kilograms, because they won't cancel otherwise. So how do you change grams into kilograms? The easiest way is to use the factor. How many kilograms are in a gram? Let's turn it around. How many grams are in a kilogram? 1,000, 10 to the third. So that means every gram is actually 1,000th of a kilogram. So that grams times 10 to the minus third is kilograms. right? Don't forget that conversion when you do your calculation, or you'll get a horribly wrong answer. You'll be off by 3 orders of magnitude. Okay, so now the kilograms cancel, and look what we're left with. Moles of our solute. Fits right in there. All right. So what's 8 times 1.538? All right, 1.538, and then 8 with an exponent of -3. So I get 1.23 times 10 to the -2 moles. And that's moles of benzoic acid. Okay? Now it's simple. Actually, we could make it simpler, but it requires some more math. And I'm trying for understanding now, not for math gymnastics. So, for the molecular weight, if we have 1 gram, and that 1 gram is the same as that many moles, there we have our calculation, right? So we'll divide this into 1, which is what? The inverse, right? 1 divided by the number. So I just hit the inverse key. And that's 81.3 grams per mole. Whoa. That's way off, isn't it? Right? Wasn't it supposed to be accepted value? Accepted value for benzoic acid is 122, right? So the numbers I picked are way wrong. Okay? But suppose we do that, right? And let's just exercise percent error. How would we calculate percent error from that? Right? Percent error is experimental value minus accepted divided by accepted times 100. Now, sometimes we don't care about the sign, you know, whether it's negative or positive. We just want how far off is it, right? If you use this one, it tells you positive or negative, right? So this is going to be negative, right? Put that one there and subtract 122 from it, you get a negative number, which says our calculated value, our experimental value, is way low by that percentage. But if we don't care about that, then we just say this, and then whatever the value happens to be. So 81.3 minus 122 divided by 122 times 100 is equal to what? I think it's still in my calculator. Yeah, I better put 81.2 minus 5. I get minus 33%. Or since we're absolute, so we're 33% off by that calculation. But the method is the same. Right? In fact, I'm going to let you do the pre-lab question, right? Because I just did one of those calculations exactly the same way we would have done it for the pre-lab question. So you do the pre-lab question using that method, right? So now you wished you'd paid attention, right, when I was doing that. So you're going to have to go back and watch it again. Okay. So now, we've got the answers we need. Drawn the graphs, which are worth 10 points. Right? It says so right here. And then you have laboratory questions. Maybe I'll help you a little bit with the lab questions. How about that? Since I took away your pre-lab points. I'll help you with the lab questions. All right. So, lab question 1 is what? Well, if you've got a copy of your method in front of you, I wouldn't have to read this, but I'm going to do it anyway. Suppose your thermometer reads 1 degree centigrade high every time. Your thermometer is off by 1 degree centigrade high. That's called a systematic error. Happens the same way every time. Those are probably the easiest ones to correct for. If you know it's a systematic error, you can make corrections in your data to account for that. Right? So those are easy. The ones that are hard to deal with, and that's why one of the reasons that the monstrous discipline of statistics has ballooned, is to deal with random error. Right? Random error, you don't know how it's going to happen. There are various theories as to whether random error has this certain distribution, right? Does it have a normal distribution, or does it have a chi-square distribution, which would be kind of like this, right? Or whatever distribution it has. So you actually have to make some assumptions in order to correct for random error. But this is a systematic error. It happens that way every time. So every time you measure a temperature, it's 1 degree high, right? So the question is, how would this affect the molar mass calculation of the solute, or benzoic acid, right? How would it affect it? Okay, I've given you time to think. Suppose your initial temperature was this, right? Your freezing point. Let's say the final temperature, freezing point temperature, in other words, the one with the solution, both components, minus the initial temperature is that value, right? That's the pure solvent. So you get a value, and actually it doesn't matter. So you get a change in temperature, right? Okay. What if each one of these is wrong by 1 degree high? What would that look like? Well, if this is the true temperature, then the one that you get is going to be this one plus that one, right? 1 degree. And this one is going to be that plus 1 degree. All right? What does that do to this value? Well, look what it does. This minus that, this, plus that, minus this, minus that, right? Minus propagates through the parentheses. Right? There's a plus, there's a minus. Does it make a difference? No, it doesn't make a bit of difference. Right? So there's an easy 3 points. Now, all systematic errors are not like that. That's one type. Some systematic errors take a little more finagling to get to correct for them, but they're still correctable. Okay, number 2. Actually, I've given you the answer to this one already. Why is molality used instead of molarity for doing these colligative property studies? Why do we use that one and not that one? You should be able to answer that. I'll give you a hint. Mass versus volume. Three. What are some possible sources of error in this experiment? Well, you need to think about it, right? Where could you possibly be? Well, I'm thinking safety. Let's think safety first, right? Right. Safety is always first. Where could you possibly be injured during this experiment, right? How about boiling water or a hot plate, right? Temperature. How about benzoic acid and lauric acid? You could get some skin irritation from benzoic acid, but it's highly unlikely. We'll just wear gloves, okay? The real possibility of injury, particularly with benzoic acid, is if you inhale dust particles, right? Benzoic acid, dust. Then it could damage your lungs. Let's see, where's some other safety? Oh, we're using glassware, aren't we? Right. The thermometer is made out of glass. The boiling water bath has a glass beaker. Right? And the tube is made out of glass. In fact, the tube that we were going to use is very, very expensive glass. I didn't have any Pyrex tubes that big. Well, I take that back. On the Logan campus of Southern, we do have Pyrex tubes. Right? If I were going to do this at New River, I would use some tubes that I inherited from a former my research career, and they are very expensive. They're made out of Vicor. Okay. But that's neither here nor there. You could break the glass, right? And that could be a problem. So you want to, that's why you wear your lab coat, you wear eye protection, you wear gloves, you wear closed-toed shoes with solid bottoms, right? You're not wearing your house shoes to the lab. Because if you get broken glass on the floor, step on it, it go right through your foot. So those are the safety issues. Now let's talk about experimental error. Where could you experience error? Right? Where could you have error? Well, let's see. Let's look at our instruments first. Water's going to boil. That's no big deal, right? It gets hot. We just want it hot. We don't care what temperature it is, as long as it's really hot. But how about the thermometer, right? Well, we've already discounted systematic error, right? But where could you experience random error with a thermometer? Right? Now we're not talking about the instrument anymore. Now we're talking about the observer, right? Because anytime you read a scale, right, there's our thermometer. Anytime you read a scale, the position of your eye matters, right? Because you've got the fluid in here, but the markings are out here, right? So if your eye is up here, then what are you seeing? You think that you're looking at the level down here, when the level is actually up here. That's called parallax error. That's why when you read glassware, your eye always has to be level, or like that, level with the glass. And some glassware is designed to help you accomplish that. Right? Volume measurements. in graduated cylinders or burettes or pipettes, periodically, this could be any tube of glass, periodically they have markings that go completely around. You have markings in between, and then you'll have completely around. The reason they're there is so that when your eye is here, you see a single line straight through. If you see a single line, you know your eye is level. If you were off like this, you would see this line and that line separated. Like you see a double line, then you know that you're not level with the measurement. So parallax error is a possibility in your measuring. What's another one? Where else are you making measurements? On an analytical balance, correct? Right. So you need to be sure that when you measure the lauric acid and later the benzoic acid in the balance, everything you measure into that container, we would use a plastic weighboat probably, everything you put in that plastic weighboat stays in that plastic weighboat while you measure it. If you accidentally, your hand shakes and a piece of the material ends up on the pan and not in the cup, in the weighboat, then you're getting the mass of both, but when you go to put it in your tube, you're not putting all of it in the tube. You left some of it on the balance, right? So that would come under the general category of spillage. Right? You don't have what you think you have. Where else could we make an experimental error? You know, those are the big two. I'll let you think about it. So that means you're going to have to go through the method yourself, step by step, and understand what's being done in order to answer that last question. Thinking as you go, where could we make a mistake at each one of these steps? Okay? All right. So I think that's everything you're going to need to do the calculations. I showed you how to do one of the calculations already. All right. Okay. So hopefully this video will be much better quality than the first one. I'm on a steep learning curve and producing better quality videos, I hope, at least so you can see what's happening on the board. So, good luck, and as I've said in emails before, the deadline is there to help you turn your work in soon enough for me to grade it before the end of the semester. There won't be any penalties for late submissions, except for the penalty of the registrar imposes we have to turn our grades in by a certain date. If you turn your work in too late, I won't be able to grade it, and you get a 0. Right? So keep that in mind. If I run out of time, then you run out of a grade. Okay, that's that.